So this is part 2 of section 8.1. And if you guys remember, we were talking earlier about these hypothesis tests and how the alternate hypothesis could take one of three forms. There could be a left-tailed test, a right-tailed test, or a two-tailed test. So this is where we're going to talk about that a little bit, like what it means in each of these cases. So the first case is a left-tailed test, and that is when you have this situation right here where you have the null hypothesis is that the population mean mu is equal to k, and k is going to be some number. And then the alternate hypothesis is that the mean is actually less than k. So this is a case where you have some reason to believe or some evidence that you believe that the mean is actually less than the stated value. So it's called a left-tailed test because of the way we're going to do this. So this would be like the problem that we did. The problem where we left off with the local health club. And we ended up getting a z-score of -2. We got a p-value of 0.0228. And we were over here. We had this z-score of -2, and we were over here in this area. So like in our case, our z of x bar, that was a -2. So this would be like the test statistic we found from the sample. So let me just mention a few things here. So this little z sub x bar is the test statistic. It's actually the z-score of the test statistic from your sample. So in the example that we did, our test statistic had a z-score of -2. And so the p-value is just the probability that z would be less than -2 or less than or equal to. Again, it's continuous, so it doesn't matter if you put the less than or the less than or equal to. So this p-value, if you remember, p, do you remember what the p stands for? P stands for probability. So on the curve here, we would have this, this z-score from our sample, which would be over here somewhere. So you'd have this z-score here from your sample. So for ours was -2, like I said in that example. And then this area under the curve is the p-value. So we can interpret the p-value as the area under the curve. We can also interpret it as the probability that we would get that sample that we did if the null hypothesis was really true. So we can also interpret it this way. It is the probability of getting a test statistic So a test statistic is like the sample test statistic. It's just that x bar value that we got from our sample. So it'd be the probability of getting a test statistic as low or lower than x bar. So the probability can be interpreted as the area under the curve, and so that's where this comes from. So if you have a left-tailed test, basically you're just finding this probability, and the way you do this, we would answer this question. So to find this probability, I'll use a different color here so it's less confusing, we would say to figure this out, we would say equals normal CDF. And because it's left-tailed, it's going to be -10, and then whatever that z-score is from our sample, which in our case is -2. So every time you have one of these null hypothesis where mu equals k, and the alternate hypothesis where the mean is less than k, whenever it's a less than, we're going to have this normal CDF because it's going to be a left-tailed test. We're over here. So to find the area under this curve, we have normal CDF with -10, right, to whatever our z-score is for our sample, because we're going to be getting this area. So it's called the left-tailed test because of that. And then the right-tailed test is the same idea, but this time we start off and we've got our alternate hypothesis. This time, we believe that the mean is greater than this stated value, the value stated in the null hypothesis. So if you look at this, we've got z is greater than the z-score we get from our sample. So to figure this one out, we would use normal CDF. And just to think about what's going to happen, because it's going to be a greater than, we're going to be over here somewhere. So we're going to have some sort of z-score over here. And we're going to be finding this area in the right of the curve, or in other words, in the right tail, which is why it's called a right-tailed test. So we're going to use normal CDF, and we would start with our z-score and go to 10, right? Because we are now in this part of the curve. So we're finding the probability of getting a test statistic as low or lower than the one we got here. Remember, don't let the words get too jumbled up here. This test statistic is just the X bar value we get from our sample. Our mean, the mean of our sample, right? That's a sample statistic, and it's from our test. They call it test statistic because it came from our sample. But it's just the test statistic, it's a sample statistic. It's the one that we had from our example. We had X bar equals 9.2, right? We had a sample mean of 9.2, and that corresponded to a z-score of -2. So this is stuff that we're familiar with. So we just have to know if it's a left-tailed test. We're finding the area under here just using chapter 6 techniques. Over here, right-tailed, we're going to be over here using chapter 6 techniques. And then a two-tailed test. This one can be a little confusing. So let me make a note of something else. Again, in this case, here's our p-value. So right-tailed test, the p-value is the area under the curve in the right tail. And, of course, it's also the probability of getting the sample that we got if the null hypothesis is true. So the one that we don't see as much, but it does come up sometimes, is a two-tailed test. And you can recognize a two-tailed test by the not equal to. So we're saying we don't believe that the mean is equal to this stated value from the null hypothesis. We're not saying it's greater than that or less than that. We're just saying we think it's different. Not equal to means different, right? So we're going to use this other type of test, a two-tailed test. And what you'll notice right here is 2. There's a 2 here. It only happens with a two-tailed test. And it's because of this. So what we'll do is we will end up getting a z-score, just like normal. But this time what we're going to do is we're going to put the positive z-score here, and there's going to be a negative z-score over here. It's going to be the same z-score, but the opposite sign, negative z sub x bar. So the p-value is the area under the curve, so this means this is half of the p-value. That's half of the p-value. And here is the other half of the p-value. So to find the p-value, what we do is we find the probability that z is greater than our z-score from our test statistic, which would be this. We find this area, then we double it. So just think if you're using normal CDF. Normal CDF, you tell it you have a starting point and a stopping point. So you can't tell it to start here, stop here, and then start here again and stop here. So with normal CDF, we find one of these and double it. So this is saying to find this one. We could just as easily find this one and double it. But most people do this one because they like to deal with positive numbers. So we basically are going to find the area under this and then double it because we also have to consider this area. That's where the 2 comes from. The 2 is there because it's two-tailed and we can only find one tail at a time. So what we would do to use normal CDF, well, first we need a 2, and then we go 2 times normal CDF, Z sub X bar, comma 10. Let me clean that up a little bit. There we go. Comma 10. And this right here, this thing, is finding this right tail, and then we double it because we also need the left tail. I could have also found this. So this would say negative 10, comma, negative Z sub X bar, and then double that. But it's just easier to deal with the positive numbers like this. So every time we have a hypothesis test, we're going to have one of these 3 alternate hypotheses, one of these 3. And then this is what you do each time. You use normal CDF each time because we're finding the area under the curve. And then we will go from there to come up with a conclusion. And this will make a lot more sense after we do one of these problems. So we'll kind of put all the pieces together when we do a problem. And then, section 8.2 and 8.3 are all going to be very similar. So once you get this idea down, the same ideas apply throughout chapter 8. Okay, so then we've got to deal with these errors. So you have to be able to deal with these types of errors that come up. And what you probably want to do is, for the errors, read types of errors if you get a chance. Types of errors on page 444. So there's 2 types of errors that we're going to talk about. So if we reject the null hypothesis when it is actually true, we've made a type 1 error. And a type 1 error, the easy way to think of this is you reject a truth. A type 1 error in statistics or in science in general, in research, a type 1 error means you rejected a truth. So we rejected the null hypothesis, but it was actually true. Now the reason we do that is because we're just going to follow the probability. But just like when we were dealing with confidence intervals and we don't know for sure that we're right, we just know that we're probably right. Right? We use those confidence intervals to deal with that. The same sort of thing is happening here. So sometimes the probability is going to say reject the null hypothesis, but it's actually because we have a weird sample, and actually the null hypothesis is true. So that means we've made a type 1 error, and of course we don't know we've made a type 1 error because we really don't know for sure if we're making the correct decision. We just know that we're normally going to make the correct decision. But it's just like chapter 7. In reality, we're not going to know the population mean. So type 1 error is when we reject the null hypothesis, but it's actually true. Okay, so there's another type of error. There's a type 2 error when we accept, or in other words, we fail to reject the null hypothesis when it is actually false. And that's a type 2 error. And that is when we accept a falsehood. So we see that the null hypothesis is actually false, but we fail to reject it. So it's like we accept it. That's a type 2 error. And the whole key is we won't know if we've made an error. We only know the probability of making an error. Okay, so that'll sound kind of like chapter 7. It's similar. We're not going to know for sure if we made an error. We just know the probability of making an error. Sometimes students ask about what kind of error is worse, and that really depends on the circumstances. And there's always a trade-off involved, because what we'll see is that if you make a type 1 error less likely to happen, then what you're also doing is making a type 2 error more likely to happen, and vice versa. Here's an example. Spam filters. So the null hypothesis is that any particular email message is not spam. Your spam filter looks for clues that can be used to reject that null hypothesis for any particular email, such as it will look for phrases such as "my dearest friend," which is going to be one of those "I have a bunch of money to put in your bank account," those kind of messages, or mail enhancement, or there's a bunch of phrases like that it will look for. So a type 1 error would involve screening out an email message that is not actually spam. And a type 2 error would involve letting spam through the filter into your inbox. So given the cost of missing an important email relative to the cost of getting the occasional message about herbal vitamins, most people would probably err on the side of allowing type 2 errors. There's also a handout that I will give you probably when we do section 8.2, which is a courtroom analogy for hypothesis testing. And in that analogy, it turns out that a type 1 error is worse than a type 2 error. So our system is set up so that type 2 errors will be more common. And that will make sense when you get that handout, and it's called Hypothesis Testing Courtroom Analogy. Another example maybe is like cancer screening. There's a lot of different tests for early detection of cancer. So the null hypothesis for anyone undergoing this kind of screening is that no cancer is present. So null hypothesis, no cancer is present. The screening is used to reject this null hypothesis if the results are suspicious. And the assumption has always been that a type 1 error is far preferable to a type 2 error, which would be kind of like a false negative that misses a cancer diagnosis. But in this class, we don't really get into a lot of different examples of these errors, but we just have to know that basically a type 1 error is when we reject the null hypothesis when it's true. Or in other words, we reject a truth. And a type 2 error is that we fail to reject the null hypothesis when it is in fact false. Or in other words, we accept a falsehood. Another thing we have to be aware of is what's called the level of significance. So the level of significance, or if anybody recognizes that Greek letter alpha, the level of significance, or alpha, is the probability of rejecting H naught when it is true. This is the probability of making a type 1 error. So we're going to know the probability of making a type 1 error. The power of a test. So this part here we don't talk much about. It takes some higher math to really get into the details of the power of a test or the probability of making type 2 errors. So we just mention them, and that's about as much as as far as we go with this. And you'll see it in the book too. It's mentioned, and then there's really nothing beyond that. So the probability of making a type 2 error is denoted by this Greek letter, beta. And the power of a test is 1 minus beta. And this is the probability of rejecting H naught when it is in fact false. In other words, that's a correct decision. Sometimes you'll hear things like a particular statistical test has more power than another statistical test. And this is what it's referring to. It's just, it would have a better probability of rejecting H naught when it is in fact false. But that right there is about as much as we'll even talk about power of a test or the probability of making a type 2 error. So we'll talk a lot more about this right here, because this is stuff that will be more important to us, and we can understand it much easier, and it's more useful in general. So that's what we'll concentrate on. So pretty much every one of these problems in chapter 8, we're going to come down to this conclusion. And we have to be able to conclude this statistical test. And it's going to come down to this. If the p-value is less than alpha, we reject the null hypothesis. So what we're going to do every time we do one of these statistical tests, we're going to calculate the p-value. We're going to look at alpha, which will always be given. And then if the p-value is less than or equal to alpha, we reject the null hypothesis and we say that the data are statistically significant at the level alpha. What about this? Who now is saying, yeah, I kind of like the sound of that. Data are. Data are. You guys ready yet? Data are. Probably some of you are still on team data is, but I still have time to switch you over. So the other thing that could happen is you could look at the p-value and see that the p-value is greater than alpha, in which case we do not reject the null hypothesis. And then a little note here is the result is called statistically significant. If it has been predicted as unlikely to have occurred by chance. So we've got a couple of notes here. If alpha equals 0.05, then we say we are using a 5% level of significance. Alpha equals 0.01 is also popular. These are pretty much the only two we'll see. We use a 5% level of significance and a 1% level of significance. And you'll see that this alpha is kind of like a line in the sand that we draw. So it'll make sense when we get into how this works. But these are pretty much the only two that we see, 5% and 1%. And you'll see in research, mostly you see 5%, but you do see 1% sometimes too. So when you're using this 5% level of significance, this is what it means. In 100 similar situations, H0 will be rejected on average 5 times when it should not have been rejected. And that is just based on random samples. Because sometimes when you get a random sample, it's just going to be an unusual sample and it won't really reflect the population much, and you're going to reject H0 when you shouldn't have. And it's just like chapter 7. Sometimes we're going to be wrong about a conclusion, but we won't know that we're wrong. Right? We're going to be right most of the time, but sometimes we're just going to get a weird sample and we're going to be wrong. So that's why follow-up studies and repeating experiments is important in science, so that if there is something that goes wrong, it'll be found later. Then there's another part that's really important that we have to understand here. And like I said, once we do a couple problems here, I'll emphasize this a lot. But we in statistics and in science and in research are not in the proving business. So this is an important idea here. I'll put a little star here. So if we fail to reject, or in other words, we accept the null hypothesis, we are not proving the null hypothesis is true. We never prove anything. We're saying that based on our sample, it appears that the null hypothesis is true. But we know we could have a weird sample, right? We could be wrong here. So we never prove anything. We don't prove or disprove. We just go where the evidence leads. So we're saying that the evidence, now our evidence is the sample data, right? The evidence that we look at is our sample, the data from our sample. And we're saying that that evidence is not strong enough to justify rejecting the null hypothesis. So we're not proving it true. And when we do reject the null hypothesis, we're not proving it false. We're not proving anything. We're just saying that the data suggest either accept H naught or reject H naught. And that's about as strong a statement as we can make. And there is also something here, page 446. When you get a chance, take a look at this part called Basic Components of a Statistical Test. And it's kind of like a summary of these notes. So when you get a chance, go ahead and take a look at that. And now it's the moment you guys have all been waiting for. We're ready to try one of these problems. We've got a pretty good one on page 453, number 21. So let me make a little room here. We'll start this one. This is number 21, page 453. And for these problems, the directions start on page 452. They're at the bottom of page 452. And it says for problems 19 through 24, please provide the following. And there's A through E. So they give us a bunch of stuff to talk about, and they're all the same for all the problems. So for this one, page 453, number 21, it's talking about these hummingbirds. And it says that in a remote part of the Grand Canyon, a random sample of 6 of these birds was caught and weighed and released. And the weights in grams were, and they give us these weights here. So I just write these down. We've got, these are weights in grams: 3.7, 2.9, 3.8, 4.2, 4.8, and 3.1. So think of, here's our sample. We've got this sample of data, and it says that the sample mean is 3.75 grams. And it says, let X be a random variable representing the weights of these hummingbirds in this part of the Grand Canyon. We assume that X has a normal distribution. Okay, so we know that the weight of all of these birds is normal. Right, so that's helpful for us because look at our sample size. It's only 6. All right, a sample size of 6. If we didn't know that we were sampling from a normal distribution, we wouldn't know that the means of all of these samples laid out in a normal distribution. But now that they said this, we know that if we took this sample, if we kept sampling these birds, and we lined up all these means of these samples on a number line, and put all these numbers down and kept going, we get a nice bell-shaped curve because we're sampling from a normal distribution. So if we didn't know this, we would need a lot more birds, right? We would need 30 of these, at least 30. But small sample is fine because we're sampling from a normal distribution. And they also tell us that the population standard deviation is 0.70 grams. So the question is, do the data indicate that the mean weight of these birds in this part of the Grand Canyon is less than 4.55 grams? And the 4.55 comes from, it mentions in there that for the population of hummingbirds, the mean weight is 4.55 grams. So let's kind of walk through A through E and see what we've got. So part A says, what is the level of significance? And that has to be stated. That's alpha. And right at the very end of problem number 21, it says use alpha equals 0.01. 0.01. So this number, basically, this is what it means. We're going to start with this level of alpha. And before you do any experiment, we want to start with this first. And we're basically saying that we're going to stick with the null hypothesis unless we get a sample, here's our sample, that has a 1% chance or less of happening. If we get a sample that is that unusual, 1% or less of happening, we're going to reject the null hypothesis. So speaking of null hypothesis, that is also for part A. And the null hypothesis is what it says here. It says that, it says in the problem, it is known for the population of all of these hummingbirds, the mean weight is mu equals 4.55 grams. So that's the null hypothesis. This is what we're assuming is true. And then look at the way they ask the question. The way they ask the question determines what the alternate hypothesis is. Although you can kind of figure it out looking at these numbers. These are way below 4.55 mostly. So you'd think it's probably going to say mu is less than this. And it does. It says in the problem, it says, do the data indicate that the mean weight of these birds in this part of the Grand Canyon is less than is the key. Mu is less than, and then it continues, less than 4.55 grams. Okay, so just like before, I mentioned whenever you have these hypotheses, these numbers will be the same, right? Our null hypothesis is always equals. And look at the way the format of this. H naught, the colon, here's the thing we're assuming, right? This is what we believe so far based on the evidence that has come before from the past or from previous studies. So this is what we're believing. But we will, just like in science, if there's evidence that suggests your belief is wrong, you don't get to just keep your belief because you like it, right? If you're going to be good at science, you need to get ready to get rid of beliefs in light of new evidence. So we're going to go with this unless our sample suggests that this is true. So this is the alternate hypothesis that the mean is less than 4.55 grams. And then it says, are we going to use a left-tailed, right-tailed, or two-tailed test? Well, when it's a less than, it's pointing to the left. It's a left-tailed test because when we figure out the probability, we're going to be in the left tail of a standard normal curve. So this is going to be left-tailed. Okay, so that is all part A. And again, it's left-tailed because it's a less than problem. If this said greater than, it's right-tailed. If it said not equal to, in the book would have said different from, then it'd be two-tailed. But this is a left-tailed. So part B says, check the requirements. What sampling distribution will you use? And then it wants us to find the z-value of the sample test statistic. Well, we are going to use the standard normal. Use the standard normal distribution because we're sampling from a normal distribution and we know sigma. Just like 7.1, when we know sigma and we're sampling from a normal distribution or we have a sample size of 30 or more, we're going to use standard normal. Z-scores, right? Standard normal means we're using Z-scores. Then it says compute the Z-value of the sample test statistic. Well, our test statistic is actually this number right here. It's our sample test statistic, and we want to find the Z-score of this. So we go to our formula. And this formula is also on the Chapter 8 handout. And I'll probably talk about that handout when we're into 8.2. Point out some things we need to know. And again, remember it is, I guess I wrote this one a little different. I think I usually write it more horizontally. But basically, remember order of operations. Remember this is divided by, right? So we plug in our numbers and we will get 3.75. That's our sample mean. Minus mu, the thing we're assuming to be true from the null hypothesis, 4.55. Sigma, they told us, is 0.70. That was given, divided by the square root of n. N is 6. And just, again, be careful with order of operations and make sure that you divide right here. And if you do that, we will get negative 2.80. Now, because we have a pretty good instinct about z-scores, this is telling you something. The z-score of this test statistic is out there, right? This would be considered an outlier, which means when we find the p-value, it's probably going to be pretty small because this is an unusual z-score, which means that this is kind of an unusual sample if this null hypothesis is true. So as soon as you get the z-score, you have some kind of feel for what's happening. So then what we need to do, though, is find the p-value. So for part C, we're going to figure out exactly how likely or unlikely this is. So you go to part C, and we need to find the p-value. So the p-value is equal to the probability that x bar would be less than 3.75. And remember, less than or equal to, it doesn't matter because this is a continuous distribution. And we've already figured out that that was the same as z being less than negative 2.80, right? So think about if we were in chapter 6, sometimes the question just said, what's this, right? And we would say, well, you go to standard normal, 1, 2, 3, negative 1, negative 2, negative 3. This may be the ugliest standard normal curve I've ever made. It's definitely one of them, but you get the idea. So negative 2.80, it's over here a ways, right? So the p-value is the area under the curve right there. And we know how to do that. We use normal CDF here. So we go normal CDF, negative 10 comma negative 2.80. And when I did this, I got about 0.0026, which is a pretty small p-value. So think about what the p-value means now. Let's think about what this means. It means that if that null hypothesis is true, if this null hypothesis right here is true, then there is a 0.26% chance that we would get this sample that we got. Remember, the smaller the p-value, the stronger the evidence against the null hypothesis. Because this is saying this is extremely unlikely, right? It's really unlikely that we could get the sample we got if that null hypothesis is really true. And we did get this sample, right? That is a real sample that we got, a sample of birds. And the probability of us getting that sample, if this is really true, is very small. So, a couple things that could have happened. It could be that this is just wrong, that this is a pretty normal sample we got and this statement is just wrong. Or it could be that this is just a really unusual sample. We just got really unlucky. We caught these 6 birds and they were just really small. And if we did it 50 more times, it would not be that unusual, right? Because we just get one sample. We can't take another sample. We just get our one sample. So if this is really true, the probability that we would have got those 6 birds with a mean weight of 3.75 grams is really small. So that's what we found. We found, remember, P stands for probability. It's the probability that we would get the sample we got if this null hypothesis is true. And we know that this null hypothesis could be true, and we just got a really oddball sample. Because we know that this follows a normal curve, but occasionally we are going to get weird samples, right? So that's what we're stuck with. So what we do, though, before we even start, we have this line in the sand, 0.01. We're basically saying, before we even start, if I get a sample that's got a 1% chance or less of happening, I'm going to reject the null hypothesis. And that's exactly what happened. So for part D, what we want to do is compare our p-value to alpha. So here is part D. So part D, we say, okay, p-value equals 0.0026. And if we compare that to 0.01, which is alpha, So looking at this, we have got our p-value. We've got alpha. We've got a little box here. And looking at this, we can see that the p-value is less than alpha. Whenever the p-value is less than alpha, we reject the null hypothesis. Which means we reject H naught, right? That's the null hypothesis. So this is described in the little box on the handout from 8.1. At the end of every one of these hypothesis tests, we're going to look at the p-value and we're going to look at alpha. Whenever the p-value is less than alpha, we reject the null hypothesis. So we're saying that our sample was so unlikely to have occurred if the null hypothesis is actually true that we don't think the null hypothesis is true. Now remember, we're not proving that the null hypothesis is not true. We're just saying that based on the sample we've had, based on our sample, which had only a probability of happening of 0.0026 if the null hypothesis is true, based on that sample, we don't believe the null hypothesis is true. So in the book, we'll always ask, are the data statistically significant? Well, if you reject the null hypothesis, then they are. So to answer the book's question, yes, the data are statistically significant. So then let's see, that was for part D. So part E is the conclusion. And this is the part that gives us the most trouble. The conclusion, just like the conclusion in chapter 7, the conclusion in chapter 8 tends to give us the most trouble. But after we do this conclusion, I'm going to give you a little format that works on all of these in chapter 8. So let me just say this one first. So we have to say, we have to mention our alpha level, because we're going to see that sometimes, imagine this, imagine if we got a p-value that was, just imagine if it was, it's not, but just imagine we had one that was like 0.03. And then alpha, we know 0.01 is popular, but so is 0.05. So if we had 0.03 and we compared it to 0.01, 0.03 is bigger than 0.01. So in this case, we would not reject the null hypothesis. But if alpha were 0.05 and our p-value is 0.03, and since 0.03 is smaller than 0.05, we would reject. So we have to mention the line in the sand that was used in our experiment. We have to mention our alpha level. And we'll see that in other examples where if we pick, like if we were going with 0.01, we may get one conclusion, but then if we would have went with 0.05, we'd get a different conclusion. So we have to mention the alpha level. So for part E, the first thing we do is we just mention that. So every one of these conclusions in chapter 8 can start like this. At the 1% level of significance. So we're stating right off the bat what our level of significance was. So a lot of times this will say 5%. So in this case, at the 1% level of significance, the sample data. So remember, we had data from one sample. Some people, instead of the sample data, they say the evidence. I'm just going to say both, because what was our evidence? Our evidence was the sample data, right? So these are really the same. The sample data, or in other words, the evidence. So the sample data suggest that the mean weight, and now basically what I'm going to write next, I'm going to write H sub 1. I'm going to write the alternate hypothesis. If you remember, our null hypothesis was that the mean weight is 4.55 grams. The alternate was the mean weight is less than 4.55 grams. Well, I'm going to basically write the alternate hypothesis, but I'm going to write it in the wording of the question. So if you look at problem number 21, it says on the second to last line on 21, it says, do the data indicate that the mean weight of these birds in this part of the Grand Canyon is less than 4.55 grams? And we're basically saying yes. So I'm just going to write that. I'm basically going to write H sub 1, but in words. So I'm going to say the evidence suggests that the mean weight of these birds in this part of the Grand Canyon is less than 4.55 grams. So if you look at what I just wrote here, this whole thing, that whole thing is just H sub 1 in words. That's the alternate hypothesis in words. And I got those words right from the question. So sometimes students struggle with the words, but remember, we're just saying H sub 1 in words. H sub 1, if you look earlier, we had H sub 1, we said H sub 1, mu is less than 4.55. These words up here are just these in words, and I'm just using the same words from the book. So when you write one of these conclusions, it kind of fits into this format. We first mention the level of significance. Then we say something like, the data indicate, or the data lead us to believe, or the evidence suggests, something along those words. Remember, we're not proving. We don't say the data prove. We are not in the proving business. We don't ever prove anything. We just are led to our conclusions by the evidence we have, but we're always ready to change our mind in light of new evidence, right? So in the conclusion here, also look, when you look in here, we're not saying anything like we reject the null hypothesis. We're just basically saying what our conclusion is, just in words, right? And it'll be more clear as we do more of them. But I'm going to show you a format that works on all of these, and it'll make it a lot easier. Because when I first started teaching this is the part that students struggled with the most. And I have this little format that kind of makes it easy. So here's the wording you can use. Okay, I'll maybe put this in, I'll say in wording. This will work on all of these problems in Chapter 8. Basically, just say this. We say, at the alpha level of significance, right? We can start up every one of these conclusions with this. And just remember that this will be 1% or 5%. And we just say, the sample data or the evidence. You use one or the other or both. And now there's two things. Number one, if you reject, so in other words, if you reject, go here. Remember, you reject when the p-value is less than alpha. So if you reject, you just say this. Suggest that H sub 1. And you just say whatever H sub 1 is in words. Whatever the null hypothesis, whatever the alternate hypothesis, you say in words. And the only other thing that could be is if you fail to reject, and I should say H naught. This too, if you reject H naught. So if you fail to reject H naught, in other words, the p-value is greater than alpha, then we just say the sample data do not suggest that H1. And you notice that Both of these conclusions are in terms of H1. I'm only doing it this way because this is the way our author does it. So when we do more examples, I'll show you that you don't have to write it in terms of H1, but the back of the book always does. So I do it too, just because it's kind of confusing if I switch these around. So I'm going to stick to this structure throughout chapter 8, and we'll all have the same structure. It makes it easier to learn, and you can answer every one of the wording questions throughout chapter 8 with null hypothesis test. You can answer all of them just like this. You don't have to answer them like this, but this is the way our book does it, and it will work every time. So 8.1 is kind of a big section, so give them a try and let me know if you have any questions.